Okay. Hello and good morning, everyone. So welcome to our first keynote today. It's a pleasure for me to introduce our first keynote speaker, Daniel Romero. He's an assistant professor at the University of Michigan in information, computer science, and complex systems. Daniel received his PhD at Cornell University Center of Applied Mathematics, where he was supervised by John Kleinberg. Before coming to University of Michigan, he was a postdoc at Northwestern University Institute of Complex Systems, working with Brian Uzzi. Daniel's main research interest is in the empirical and theoretical analysis of social and information networks, and he is particularly interested in understanding the mechanisms that involve the network evolution, information diffusion, and interaction among people on the web and in complex organizations. Please join me and welcome Daniel.
All right, can everyone hear me okay? Great. Well, thanks, Claudia, for the nice introduction, and thanks for to the organizers for inviting me. It's really a pleasure and an honor to be here telling you about my research. So I also want to thank my collaborators, like up front, they're listed here, and also the NSF for giving us money to do this. So what I want to talk to you about today is a topic that I'm very interested in, and is the idea of studying systems, social systems of different types, that are exposed to exogenous shocks. So things that happen outside of this social system that can potentially affect the people in the system, and I want to know how the systems react, how long these changes last, and so on. And so today what I'm going to do is I'm going to give you two examples of this kind of thing. So the first one is going to be on a social network. And the question on a social network is related to the question of the studies on social network temporal dynamics. So what happens to a social network as it evolves over time? And I think we know a lot about this type of question already. So for example, we know that networks tend to have shorter and shorter diameter. They tend to densify. They tend to grow to have a heavy tail degree distribution. And these findings have been very important because they've allowed us to do things that are really useful, like doing link prediction, like finding influential nodes, like finding communities, and so on. But I have a question that's related, but it's slightly different, right? So I have a network here at time t equals 1. And then it evolves to do whatever networks do, and at time t equals 2 it looks like this. And then something happens outside of this network that affects the nodes in the network, and I want to know, how does the structure change? What is this network going to look like at time t equals 3? And this question, of course, can be asked for not just networks, but other types of systems, like, for example, people collaborating, working on something, right? So they first learn to kind of like work with each other, they learn to figure out how to distribute the workload, and so they start to do more complex tasks and so on. And then something happens that affects these people, and so I want to know, how do they change the way they collaborate with each other, for example. And so this is the kind of question that I'm interested in. And I claim that for a lot of these systems, we've kind of studied them a lot during times of normality, but we haven't really studying them as much in this kind of setting where we're asking what happens when there's some type of exogenous shock. And part of the reason for this, I claim, is that it sort of requires twice as much the data that you required before. So just you study the system, you need some data that is probably time-stamped, and we've done a lot of work that uses this type of data using online data and so on. But if you want to ask the question about the exogenous shock, then now you need data on the exogenous shock, and then you need to be able to kind of put them together. And so this is sometimes a challenge. And so let me tell you about two projects that we did and where we had like interesting data sets where we could actually do this kind of thing. So the first one was this data that we have that comes from a hedge fund. It has two parts. So the first part is the set of full records of instant messages of people in this hedge fund talking to each other. It's about 180 employees and their outside contacts. So I can tell who talks to whom inside the hedge fund, and then for each person in the hedge fund, they can invite external contacts and they join the system, and then I can also track that communication. I don't have communication among the outsiders, though. So this is about 22 million IMs. And then the other part of the data that I have is the full stock trading of the hedge fund. So what stock they bought when, for how much they bought it, and so on. for the same 4-year period. So it's about 600,000 trades. So with the first part of the data, I can use this to track the social network and see how it evolves. I can look at the structure of who talks to whom on every day. And then with the other side, this side of the data, I can ask about exogenous shocks. So I'm going to be defining exogenous shocks that come from large movements in the stock prices that these people trade. So in the talk today, I'm going to focus on this question of how does the changes in the market affect the structure of the network. We also did some other stuff that I'm not going to get into, but I want to tell you about. So this is in a paper in www last year. So we also looked at different behavioral things in the hedge fund. So for example, when they trade, what they trade, their performance, and something about the content of the IM. So for example, the type of emotional cognitive content that the IMs that these people exchange have. And what we wanted to do was we wanted to try to predict these things using signals from the social network as well as signals from the market movements. And surprisingly, what we found is that the signals from the network are actually better predictors of these things than the market movements themselves, which we thought would be very important. And so this sort of highlights the importance of understanding these structures because this tells us that at least they seem to be predictive of things that we care about. But again, I'm not going to show you this part of the results. Okay, so let me tell you how we measure things. So first, to measure the shock, what we're going to do is we're going to measure the change in the stock price S on a given day D, just the relative change, closing minus opening over opening price. And then what I'm going to do is I'm going to take stock S on a day D, and I'm going to define a graph among the employees who mention the stock S. So let's say here is the full network of all the nodes in the hedge fund and who talked to whom on this given day. Let's say the red nodes actually mention the stock, and now I'm going to take the graph induced by the red nodes, and this is going to be my graph GSD. And now I'm going to ask a number of things about the features on this graph. And so what kind of features am I going to be looking at? Well, first, very naturally, I'm going to look at how big it is, how many nodes, how many edges. And then I'm going to look at some more interesting things. So for example, I'm going to look at how dense it is. And to do this, I'm going to look at clustering. So how many triangles does this graph have? Could have a few triangles like this, or with the same number of edges, they could cluster a lot more, form a lot more triangles. So in this case, they're choosing to talk to people with whom they share lots of friends. In the other case, they're kind of expanding more. They're looking out further away from their local neighborhoods. I'm going to also look at the tie strength. So I'm going to split the edges into weak and strong, and I'm going to ask, are there lots of weak edges like this, or are people choosing to talk more with their strong ties like this? What I'm also going to look at is I'm going to look at what we call openness, which is how much communication is happening with people outside of the hedge fund. Like I said, we can track that as well as the insight. So I'm going to define these border edges to be edges that are going outside of the hedge fund. So here the circle is the hedge fund, and so how many are crossing the circle? And so the network can be have lots of communication going outside like this, or they could be focusing their communication internally, right? And when you sort of think about the types of structures that these features can produce at the extremes, you realize that there are sort of like two options. So one is what we call this turtle lap network. So imagine a turtle pulling its legs and its head inside its shell. This is what this network is doing here. So it's lots of internal communication as opposed to external. People are choosing to talk to their strong ties, and people are choosing to talk to others with whom they already share lots of friends. On the other extreme, you can imagine that the network is more expansive, so people are talking more with people outside of the company. They're extending out to weak ties, and they're talking to people far away from their local neighborhoods, so that they don't share lots of friends with them. And when we try to think, like, what should we expect to see when there are these exogenous shocks, which type of structure do we think is going to occur? And we look in the literature for hints, we kind of find sort of arguments for both. So we have these competing hypotheses, and so let me just go over them quickly. So for the turtle lap network, you would say, well, people want to talk to other people who they already trust, and these tend to be my strong ties, the people who I already share lots of friends with. Also, if I'm looking for very specific information, then I need to know what they know in order to ask them, so I tend to know, well, my strong ties. Also, from the threat rigidity theory from organization theory, which applies to organizations and says when they're faced with some type of external threat, these organizations will tend to stick to what they know how to do best. They will not innovate. They will do sort of what they always do. And the network version of that would say, well, then these people should be talking to their strong ties because that's what they usually tend to do. Actually, this threat rigidity theory will come again in the second part of the talk, so there are other things that it says that I'll mention later, but it's kind of interesting that it kind of shows up in both. All right, so that's kind of like the argument for the turtle up version. Now, there's another argument to be made for the expansive version, and it's more of a sort of strategic argument for how these people may behave. So you may say that, well, as we all know from Granovetter, if you want to have new information, you have to go and talk to your weak ties because your strong ties you already know everything that your strong ties know, so you're not going to find anything new there. And also from structural holes, you know that if you kind of try to kind of go far away from your local neighborhood, then you may be sort of expanding different communities, and this will allow you to have diverse information, which ends up being really useful in times of uncertainty. So if these people are sort of being strategic about this, then maybe you expect that they'll, talk a lot with the outside, with their weak ties, and they won't form lots of triangles. All right, so this is this kind of the setup, and now I'm going to show you what we actually find. Okay, so I'm going to be showing you plots like this, which have, on the x-axis, have the change in the stock price. So we have 0 in the middle here, so that's like no change in the stock. And then the y-axis, I'm going to show you the network features. And I'm going to roughly call them their name, but there are a number of like normalizations that we have to do because we're doing all sorts of weird things, like we're aggregating over all the stocks, but some tend to be more popular than others to begin with, so that kind of like messes things up. And also some of these features are kind of correlated with each other, so we have to do a number of controls. But I'm going to hide all of that. I can tell you about them offline, or you can see the paper. I'm just going to tell you what the feature is. So for how big these graphs are, well, here's what happens. When there's a big change in the price, then more people talk about these stocks, which makes sense, right? Those graphs get bigger. Okay, so now let's go over the more interesting one. So what happens to the clustering coefficient, right? Do they tend to look like this or like this? And what we find is that actually there's an increasing clustering coefficient. And actually it doesn't matter in which direction the price is going. There's always an increase in the clustering coefficient, whether it's negative or positive. Okay, let's look at the tie strength. So from the clustering coefficient, we kind of see a hint that maybe we're going to see the turtle up version of the network. And so for the strength of the tie, what I'm going to do is I'm going to label each one of the edges xy to be k strong if x is among the top k most frequent connections of y. And I'm going to show you the result for k equals 5%, although at the end it doesn't matter. If you choose a reasonable k, you get this similar trend. And if this is sort of consistent with the clustering coefficient, then you'll see that these edges will have to become strong as you kind of move away from 0. And that's kind of what we see, at least initially. I mean, when these prices get really large, the error bars get larger because there's less data there. But as we kind of move away from 0 initially, you do get these, like, these are getting stronger. So people are choosing to talk to their stronger ties. And then for the openness one, this is how much external communication there is. We should see that these edges sort of drop down if we're going to have, again, the complete evidence for the turtle up version of the network. And that's what we see, right? So they start to have more and more internal communication as these prices get, these changes in prices get larger. So overall, we see kind of this very clear picture that the network is looking like the turtle up version of the network with higher clustering, stronger edges, more internal communication, which is consistent with the first arguments around trust and expertise, knowledge, and threat rigidity. So what this suggests, like I said, is that, well, these systems are definitely reacting to these types of exogenous shocks. And as I was telling you, these things end up being predictive of important things, which highlights why we should try to understand them. Okay, so that sort of ends the first example of looking at exogenous shocks in social systems. Let me now go into the second example, which is in a completely different setting, and it's Wikipedia. This is based on a paper we had this year in IC2S2. So what are shocks in Wikipedia? There are many different kinds of things that you could imagine would be happening in Wikipedia that could be thought of as shocks. And what we pick is we pick one specific setup that's kind of interesting and very clean. And it is looking at the censorship block of Chinese Wikipedia in mainland China. Because what happens is that when China blocks Wikipedia, especially for the first time, then you have all of these articles that all of a sudden lose a number of their editors, and we want to know how do the remaining editors react to this surprising exogenous thing that happened. And so, well, so let's talk a little bit about what we should expect. And sort of this motivates some of the features that we actually look at. So what we thought we would expect is first, we should see some decrease in activity, overall activity, for many reasons. Probably the most compelling reason is that, well, if you're editing Chinese Wikipedia, and now you know that Chinese Wikipedia is now blocked in mainland China, then even if you are not in mainland China, you may not want to edit so much anymore because who's going to read this stuff now? A huge, percentage of the population who would read this is now blocked. So probably we would see some decrease in activity. And then if we go back to this thread rigidity theory, which kind of is like the theory that keeps on giving, it also has some sort of interesting predictions. So first, in organizations, they tend to see that when there's an external threat, the organization tends to become more centralized. So fewer people making all the decisions, so now the CEO is really in charge and everybody else has no say. And actually seem okay with it because there's more cohesion, because everybody perceives this sort of external threat, then they kind of feel like they're being attacked by this external thing, and so that brings more cohesion and less conflict. So what we're going to try to do is we're going to try to see if we can see evidence that these kind of things are happening in the Wikipedia setting. Now, here's some timeline of the sort of like what has been happening with Wikipedia in mainland China. So it actually started in 2002. That's when Chinese Wikipedia launched, and had a few years to get started. Things were going really well, and then there was a really small block around 2004 that lasted only a few days, very short, so it probably didn't have a huge impact. But in 2005, there was one that actually lasted a whole year. And so this was the first time there was like a real block that lasted a long time. After that, you can see there are more. But this is the one we're going to be looking at, the first big one. And so what we're going to do is we're going to look at this date when the block happened, and we're going to look at 1 year before and 1 year after. And then we're going to compare different features in the collaborative features of the editors between these 2 years. And we're going to see how they change. We have about 50,000 articles that we're looking at, and about 27,000 of them had no editors that were blocked. So for those articles, nothing happened. For the rest, they had at least one editor blocked. Okay, so what are the measures here? So again, we have some shock that we can quantify in some way. And so here what we do is we look at each article and we ask, what is the fraction of edits that were contributed by people who were blocked? And this is going to be the shock, right? So the idea is that if you block people who are very active, then that's going to be a sort of a bigger shock of a bigger intensity than if you blocked a few people that weren't as active. And then to measure, this thing is not. All right. And then to measure the different features, again, we're going to take a number of measures, and we're going to measure them in the post-block minus the pre-block divided by the pre-block to see what the relative change was. And so for activity, we're just going to look at the relative change in the number of revisions. For centralization, we're going to look at the change in the Gini coefficient of the distribution of the number of edits per editor. So here, a very centralized article would have just one person doing a lot of the work and then everybody else just doing very little. The other extreme would be that everybody's kind of equally contributing to the article. And then for conflict, what we're going to do is we're going to look at the fraction of reverts, which has been used as a measure for how much conflict there is. Usually it indicates people kind of like undoing each other's work because they're having some type of argument. We do some like basic cleanup to like remove reverts by bots that sometimes are just kind of fixing up things, like taking care of vandalism and so on. So use this as a measure of conflict. All right, and so let me tell you a bit about the analysis. So because there's this qualitative difference between the articles that had someone blocked versus the ones that didn't, because the one that had someone blocked, well, they lost someone, whereas the other ones, they may not have perceived that anything happened at all. Then we're going to do the analysis in sort of two steps. So first, we're going to just simply compare the differences between the articles that had someone, at least one person blocked, and the ones that didn't. And we're not going to care about how many, how intense the shock was. This results for this is in the paper. I'm not going to show you them. The ones that I'm going to show you, which are consistent with the first one, is I'm going to look at the ones that had at least one person that was blocked, and then I'm going to look at how changes in the intensity of the block impact the collaborative dynamics. And we're going to use linear and nonlinear models to show you this. And so here's the results. So first, for activity, here is the shock level, and then here's the change in activity. And so you see there's sort of this monotonic decrease in the activity as the shock increases, which is kind of sort of we expect very naturally. One interesting thing, though, is that if you look at, this is looking at all of the articles. If I look at only the big ones, meaning the ones that have some minimum number of editors, and here our minimum number is going to be 5 editors, then you still see a monotonic decrease, but now there seems to be this nonlinearity going on where for small shocks, these bigger sort of articles tend to be kind of resilient to them, but you know, for the big ones, then they tend to drop much faster. And so it seems like the large groups tend to be more resilient for, you know, losing just small number of people, but when they lose a bigger one, then they decrease their activity much faster. Actually, you only see this sort of difference between what happens in large groups versus small groups for activity. So for the other measures, it actually it looks the same for both. So for centralization, this is what happens. It's kind of weird that, well, first thing is, what's not weird is that you have that centralization. So this curve is always above 0, which says there's always an increase in centralization no matter how big the shock is, which again is kind of consistent with this thread rigidity theory. But what's kind of weird is that the biggest change happens for kind of intermediate values of shocks. So why should this be the case? Why would having like either a little one or a big one mean the lowest sort of change in centralization? The answer is we actually don't know exactly why yet, but we have some ideas. So when we look at the inflow of new editors as a function of the shock level, what we find is that if you lose more people, you get more new people. It's like the Wikipedia sort of compensating for the fact that you lost more editors, and therefore you get more editors somehow. And so we think that this makes a difference in how you kind of see these dynamics playing out, because these new editors, they weren't there before, so they didn't experience the shock. So therefore, you wouldn't expect them to behave like the ones that were there before and actually experience losing the rest of their members, right? And so for this reason, we think that this may sort of bring this curve down, because it's kind of driven by editors who weren't there before the shock happened. But again, this is kind of like, at this point, a hypothesis. We haven't really like done some further analysis to check this, and there are things we can do. Okay, so for conflict, again, this curve is sort of always below 0, which says that there's always a decrease in conflict, as you would expect from thread rigidity. Again, you see this sort of intermediate level of shock gives you the highest change in conflict, and again, we think is due to this inflow of new editors being different for larger shocks. And so let me wrap up now. I think I'm, probably good with time. And so let me summarize what I had told you. So in this hedge fund, we found that the IM social network appears to react to market shocks. The networks tend to become more clustered, stronger ties, and more internal communication. And then, as I kind of mentioned, but I didn't show you, these social network features are predictive of important things within the hedge fund, which sort of highlights why we really should care about studying them. In another completely different setting, we found that in Wikipedia groups, these editors become less active, they become more centralized, and they have less conflict when they're exposed to this thread, this exogenous shock. And so these are sort of like 2 examples of social systems where we definitely see them react in important ways when they're exposed to these particular types of social of shocks that I looked at here. And so I hope they serve as an invitation for you to be interested in working in this type of problems, because if we want to understand and predict and eventually control in desirable ways the social systems, we should study them in times of normality. We should know how they sort of evolve organically, but we also want to understand them in times of instability, uncertainty, or stress. And if you want to take this invitation very literally, then we are hiring, and so if you are interested in a postdoctoral fellowship to work on these kind of things, then please let me know. Or if you have students who are looking for a postdoc, please send them my way. And with that, I'll take any questions. Thank you for your attention.
Okay, I think we have time for 2 questions. First one, yes. Okay.
Thank you for your talk. This was fascinating. I'm wondering for the stock trades. I mean, it is fantastic that you were able to get both the stock trades and all that internal information from the companies. I was wondering if you could talk a little bit more about how you identify which stocks to target. Is it this, like if they're shorting stocks, something like that, are the stock prices relative to the position the company has? And is it sort of what they already have versus what they go on to buy right afterwards?
Right.
And also I'm wondering if there was any structural change in this model, since the years of 2008 and 2009 are amazing to have in this data, but they certainly had very surprising shocks.
Sure. Yeah, so let's see. So for the first one, yeah, it's a good question. So we were expecting to see that it makes a difference whether prices are going up or down, and this would be relative to the position they hold on the stocks. Actually, let me back up a little bit. So when you said, like, how do I choose which stocks to study, I looked at all the ones that they actually hold some position in. It actually turns out that it's non-trivial to say, like, at any given time, like, exactly, like, so they hold, like, different types of positions in a stock, so it's hard to, like, label it as, like, short or long for any particular one. So we didn't actually try to disentangle, like, you know, how the shock would play out if, you know, the price increases and you have a long position versus a short position. We couldn't disentangle that very well. So the results I showed you were like any stock you hold some position in, how do you see this changes? And so we're not further disentangling that. I think that would be very interesting as well. There are some results we have in the paper that looked at sort of like sentiment and the interesting thing there is that, well, when you see this sort of like U-shaped or V-shaped curves for the prices, you say, well, yeah, it makes sense because you don't always lose money when the prices go up, right? It depends on your position. But what's interesting is that in the analysis of the content, you see that positive emotions always go up with increases in price, and actually they're flat for decreases, and then negative emotions go up for decreases in price and stay flat for increases in price. So it seems like those kind of behave as if they're always hold a long position, which is not true. And so, yeah, those are kind of interesting questions that we haven't completely kind of disentangled. The other question was the year, right? So what we did do was trying to separate, like, okay, yeah, we want to make sure that this is not only a 2008 thing, which is obviously an unusual or, you know, right time. So we did, like, do the analysis separately for, like, the later years only, and we kind of saw the same kind of pattern. So it didn't seem like it was kind of, like, dependent on only being that particular time period, yeah.
Hey, Dan. Great work. I love it, as you know. I had a question similar to the last one there about the content. So in that U-shaped curve, did you look at any of the content to get a sense of whether it was one of the different kinds of emotional or cognitive mechanisms? Like, could you tell from what the turtle networks were saying that it was about trust, or that it was about expertise, or which one of those it might be that was driving the turtling?
No. I mean, we haven't done that. That is kind of like the next thing. Like, there are so many, like, okay, so now we see this, like, clear direction towards the turtle lab, and then we had this hypothesis, but looking in the data, like, why do they have more internal communication, right? Like, maybe it's not that they trust each other, maybe it's just that when this happens, they have to, like, figure out as a company what they need to do, or maybe they're within certain groups that they need to kind of, like, make a decision. So it's not like they're, like, trying to get information, they're trying to, like, make a decision on what to do. I mean, these are, like, really interesting things that we could look at trying to see, because we do have the content of the AMs, but we haven't done it yet. They're definitely trying to identify the exact mechanism that sort of, like, gives rise to this is important, and like, two directions on that is, yes, looking at the content, but also doing some modeling, right? So trying to figure out if we can see if there are these, like, sort of, like, smallest number of, like, ways that the assumptions we can make on the node that would give rise to this type of network that can explain the whole thing. So these are kind of like two directions I'm thinking about. But yeah, I don't have an answer.
Okay, great, thanks.
Yeah. Thank you. All right.
Okay, and with that, I'm glad that I can introduce you to our second keynote speaker, Milena Tsvetkova. She's an assistant professor at the Department of Methodology in the London School of Economics and Political Science. Before that, she received her PhD as well from Cornell University, where she worked with Michael Macy. She did her PhD in sociology, and afterwards she joined the Oxford Internet Institute as a postdoc. And Milena's work aims to expand our understanding about the fundamental social phenomena such as cooperation, contagion, and inequality. She focuses on identifying mechanisms that account for complex dynamics. Methodologically, she takes advantage of the research opportunities that are opened up by new computational and online technologies. And I think in her keynote today, she will talk about these new opportunities such as games and gamifications.
Thank you all for being here on the last day of the conference, for staying. I want to thank Claudia for the kind words and also the organizers for inviting me. And I particularly want to thank the organizers for having a perfectly balanced gender ratio in the keynote speakers this year. So I hope this stays for next year too and for the future. So let's talk about games a bit. So currently there are 1.8 billion gamers online worldwide, and about 700 million of them are active in the sense that they spend 3 hours or more per week playing. 48% of those are actually play social games. So now I originally thought that gamers are 12-year-old schoolboys, but then I thought more, and I realized that my mom plays like about 2 hours a day, solitaire every day. So indeed, when you look at the statistics, on average, gamers are 35 years old, and 41% of them are female. So they're relatively representative, much more than with kind of the stereotype goes. So, of course, this new reality has opened new possibilities for research, and on the one hand, we can observe how gamers behave online in these games, and this has indeed been done very successfully by a number of researchers that are here at this conference. But on the other hand, we can actually use this potential and use the interest in playing games and conduct gamified experiments with these people. So this is what I'm going to talk about here. So why do we want to do that? So to borrow actually a graph that Matt Selganik had on last talk at the conference last year in Chicago. The reason is that this allows us to pretty much bring the marginal cost per participant to almost zero, of course, not counting server costs. And this is in contrast to traditional ways to do experiments where we pay them, and even if they're on Amazon Mechanical Turk and we pay them cents, US cents, still there is as more participants come in and we want to do larger experiments, the cost increases. So of course this is not just a question of size. The size allows us to do qualitatively different studies. So we can still control the interaction online within, of course, some limitations. And this is great because experiments are best for identifying causal relationships, and that's why we want to use them. But now we can do group-level experiments. So we can have multiple large groups, which allows us to look at groups as complex systems. And this allows us to study mechanisms such as feedback loops or path dependence, something that we have not been able to do neither with survey data, observational data, or with kind of small-scale lab experiments. So what is gamification? So roughly it's the use of game design elements in non-game contexts. It's mainly used in the industry. You have all been part of it, more or less. This is a diagram designed by Yu-Kai Chu, who is a gamification consultant for the industry. And it very neatly summarizes different ways in which you can motivate people. In experimental social science, we usually assume, not all of us, but most of us assume that the right way to do it is to give them small monetary incentives. But we know that people are motivated by other things. So among those, we have, for example, kind of social influence, the possibility to exert social influence, meaning, desire to have meaning or to have a sense of accomplishment, for example, and so on. So gamification, as I mentioned, has been used in industry, still used is being used, but also it has been used in natural science, particularly to answer important questions in science. So, for example, computer science, it's been used for tagging images. In biology, games have been used to study the folding of proteins, the design of RNA molecules, and neuron mapping in cognitive science, and then also actually quantum computing most recently. So in social science, there is, I can think of one prominent example of gamification. That's when Axel Roth in the early 1980s invited a bunch of scientists to contribute strategies for the Prisoner's Dilemma game and made a contest out of it. So in a sense, that was a game where you get others to pretty much, participate in a game, in a study. Most recently, at the last IC2S2, David Lazare and colleagues presented their new platform, Volunteer Science, in which they also rely a bit on gamification elements. But unfortunately, they currently don't have the capability to have interactive experiments where there's more than one person. And now currently you can also kind of play a game by yourself or with a bot. So this is actually what I think is the possibility for future research. So here I'm going to present mainly one study based on about segregation. That's a study that was published last year, and it's in collaboration with David Sumter, who's a mathematician at Uppsala University, and some of his collaborators. And later I'm going to talk about another study that we're just starting together with Claudia Wagner and Andrew Mao, who are in the audience, and which is about inequality. And this study is sponsored by the Volkswagen Foundation, and it's going to be more about the potential rather than any results yet. So let's start with segregation. So as we know, segregation is a very prominent, very significant problem we're all facing today. You have probably all seen something similar, like this map. So this is a map of New York City, where every dot on the map is a person that lives there, and the color of that dot shows their race. So you can see clearly there is a lot of segregation in New York City, but that's a problem all over the world, not just there. So Thomas Schelling proposed a model about how segregation obtains that I'm sure all of you are familiar with. But just to make sure we're on the same page, I'll just briefly go over it. So in this model, we have agents who have a homophily, so they prefer similar neighbors, but they wouldn't mind diversity, right? So they're not bigots, they're not intolerant. And if they are in a situation where they're too much of a minority, there are not that many others like themselves, they would move to a place where they feel happier. So let's take an example of this individual in the center, currently unhappy, they're in a minority. So they decide to move somewhere where it's a better situation. But by doing that, they change the composition of their old neighborhood. So some of their old neighbors might decide to move. And they also change the composition of their new neighborhood. So some of their new neighbors might move. So in essence, every single move triggers more moves and triggers these cascades where you obtain an outcome that is much more extreme than any single individual desires. So what Schelling showed was that even if people are tolerant, you can obtain segregation. But subsequent models have shown that even if they actually actively are interested in diversity, you still obtain segregation. So Schelling's threshold function was like that, right? And in this case, we have a strict preference for diversity. So everybody's kind of best off when the world they live in is completely integrated. And even in this situation, we have basically segregation. So these researchers have concluded that public policies that promote tolerance are futile, right? So this is a very kind of counterintuitive result and a bit quite dark, I'd say. So we set out to test this prediction in particular. So what we did is that we have 4 real-time multiplayer games where the score in these games was pretty much following the utility function that people assumed in this simulation model. So we had a threshold function for what we call the same game. That was the traditional Schelling function. We had a diverse game in which there was only preference for diversity, the same and diverse, which there is both homophily and preference for diversity, and a bit of a contrived example where we have kind of a world in which you have a choice between being complete bigot or kind of like a completely fetishizing the other. And we used previous models to come up with predictions, pretty much replicating what was being found that same and diverse and same game obtain relatively high levels of segregation. So then what we did is we went to 20 different high school classrooms in Sweden, and we told them that we're going to give them a demonstration, interactive demonstration mathematical model. Like, they didn't know what this is about. And we told them we're going to play 4 games. You know, we start with 4 games. And so in these games, so this is in Swedish, but you know, basically, as in all games, your goal is to get as many points as possible. The rules will differ, but overall, that's the goal. And you're represented with an avatar that has a color and a number. You can move your avatar up, down, left, or right to the next possible location that's available. And the number of points you have depends on the number of neighbors of same color as you, where a neighborhood is defined as the 9 nearest neighbors. So you are going to have a game control that allows you to move your avatar and to look at the number of points you have and how to get higher points. And the game what you're interested in is getting the highest number of points at the end of the game, where a game ends after 2 minutes or after everybody has stopped moving. So at the end of these 4 games, we're going to show you the results. Basically, everybody's results, we're going to project them. So in essence, we gave every student a tablet that served as a game control. We theoretically could have asked them to use their own cell phones, but for kind of better control, we decided to have tablets. And so they, as I mentioned, you know, they can see their avatar and they can move it up and down, left to right, and they can see their utility and what's basically current utility, or rather current score. I shouldn't use utility here. Current score, they know nothing about utility. Current score, and then how to get the highest score. Where here on the, you know, on the kind of this axis, we have the percentage of neighbors who are similar color as you are. And then we projected on a screen pretty much like this one, right? Like where everybody was playing on the game. So let me just show you like a replay of one of these games. Here they're playing the threshold function, the original Schelling game. And in this case, they very quickly reach equilibrium. And so we actually stopped the game before the 2 minutes were over. So I'm going to stop it now. I don't have time for this. Okay. So in essence, how we implemented gamification here is that we did not use financial incentives. In fact, we were not allowed to pay high school students money. But instead, we had this social comparison where they knew that at the end of all the games, they will see their points and they will see everybody's points. We did not use any ranking system. We just showed them in random order. And we also allowed them to communicate, and also the interaction, because it was real time, it was actually very fast paced, as you could see. And so this kind of really made the environment quite exciting, quite talkative. So let's see the results. So here in these plots, in this like gray fuzzy area, showing the results from the simulation study. So that's pretty much the predictions. And the density basically of the predictions, and the dots show the empirical results we get from the different 20 groups that we got. And so as the threshold kind of function predicts, we get high levels of segregation. Indeed, that's what we observe. On top, I'm showing the level of segregation, and this is the average score. So basically, what's the kind of the average score they get, or the utility in the model. For diverse game, again, as predicted, we have only diversity, no homophily, and we indeed get integrated world. For the same and diverse game, however, we don't get the prediction. So as I mentioned before, this was the very kind of an intuitive finding that we still get, the models predict, we still get segregation, but in our case, actually, it was pretty well integrated. And actually the same with kind of surprising findings for the same or different game, because we a priori thought that everybody would coordinate on kind of this part of the utility function, because they could already do it very well in the original threshold function, right? Like where you get segregation. And so in this case, it was a relatively sparse board, so they could just like segregate in different ends, and everybody's happy. But actually what happened is that it only took one individual who decided to be in this part of the utility function to mess it up for everybody else, right? So you have like two segregated worlds, and one individual decides to actually prefer the other, and so it automatically lowers the utility of everybody else from the opposite camp. And so in effect, what happened is that they were all trying to coordinate on the alternative equilibrium, which would be a checkerboard, pretty much, so blue, yellow. And this is much harder to achieve. So only two groups managed to achieve it, despite the fact that they could communicate freely. So you might say, oh, we don't really replicate the findings. Maybe the reason is that 2 minutes were not enough for the participants to kind of converge to an equilibrium. But when we look over time, you can see that they very quickly kind of reach equilibrium. It doesn't change that much. So we don't think that's the reason. You might say, well, we didn't pay them, so hence, they were not optimized, they were not maximizing their utility or their score in this case. But in this plot, we don't see that. So this plot shows the number of seconds that the participant stays in a certain position before they decide to move. So the pinker it means that this is a preferred position, they don't want to move out of it. And so here we have on the x-axis the number of different neighbors, the number of same neighbors. And so, in essence, what we see is that in the games, indeed, people are overall avoiding positions that giving them low utility or low score, and going for staying in positions that give them high score. So then we looked at random relocation. So in this case, similarly, we plot basically the percentage of people that move out of a certain position with a certain score to another one with a higher moving score. And so usually if there was kind of an intentional movement from a kind of a low score to a high score, you expected to see kind of a like a pink below the diagonal, but that's not what we see, obviously. So in essence, what we found was that people were moving randomly, and this was undoubtedly dictated by the very fast dynamics of the experiment, because they didn't have time to evaluate the board. But I think there's also something else hidden here in the fact that to be stuck in a position that's suboptimal, you need to not be satisficing in a sense, right? So you have to recognize that there is no better position, and so you want to stay put. And so in this case, people did not have the ability to realize that. But I think also, in real life, often people might, kind of don't satisfy when they're not happy and might be willing to take like random decisions just to get out of this position. And the predictions for the same and diverse game were that pretty much, agents reach the situation where they're stuck in a suboptimal position, but there's no way, they realize there's no way to improve their utility, and hence, you get this suboptimal segregation that nobody prefers and actually everybody suffers from. And that's not what we observed in the experiment. So indeed, when we replicated the simulation studies with this assumption of lack of satisficing, so you cannot see the board, but if you don't get a high score, the highest score rather, you still move, then indeed we observe that we get now much better predictions from the simulation models for what we observed in the experiment. And somewhat too actually for the same or different game. So to summarize, in this study, what we found was that incentives for homophily produce segregation, but incentives for heterophily and local diversity prevent it. So now this is a kind of very common sense finding. It's like, duh. But, as I mentioned, it is actually against what the kind of simulation models have predicted, right? What theoretical models have predicted. And of course, in our setting, there was a very high-paced dynamics, and so this is not a good model of kind of serious decisions such as moving house, but perhaps it's not that far away from what we experience when we, for example, at a cocktail party, at a conference, or in a schoolyard, for example. So what here, this kind of first attempt to use gamification, what we learned also is that we might have this kind of perverse situation where we have incentives that we did not intend. In particular, in this case, there was this kind of behavior where people interpreted the game as zero-sum, where they thought that the way to get higher number of points is by getting everybody getting lower points. All right, and so usually that's not a problem. There are always some crazy individuals that we learn to ignore. But as we saw in the same or different game, this could be a problem because we predicted this kind of segregated world in which everybody's happy, but it only took one crazy individual to kind of mess it up for everybody on one side of the board, and so that the whole kind of world had to look for a different solution. Right, so that's something to keep in mind when you use gamification. So I'm going to next talk briefly about this new project I'm starting with Claudia Wagner and Andrew Mao, and it's on the emergence of inequality. And the puzzle we're trying to address here is, why do we observe extreme outcomes when it comes to wealth, to income, to power, to influence, to popularity? When we look among each other, we're actually not that extremely distributed when it comes to mental ability, physical ability, or psychological traits, for example. And also we know from kind of behavioral studies very well that people actually in anonymous situations have a strong preference for equity. So why do we get inequality? So kind of the reasoning goes this way. So we imagine a world in which we are interconnected, we are interdependent, and due to behavior and interaction, although we might be quite equal, there might be some inequalities emerging. The problem is that these inequalities could have differential effects on rich and poor, in a way that the poor get poorer and the rich get richer. And so in the end, we could get a much higher level of inequality. And that's what we're planning to study, in particular in much larger groups, right, in order to be able to identify these feedback loops and maybe path dependence too. And in particular, we're interested to look at what happens when certain characteristics that you achieve are visible. So, for example, your wealth or your level of cooperation or your popularity. And when you can observe that, and then you can decide who you can connect with, right? So theory kind of predicts that due to mechanisms such as homophily, discrimination, or preferential attachment, we indeed expect much higher inequality than we start with. Then we can also look at what happens when you have prominent group distinctions, and especially when one group is smaller than the other one, and especially when this might be correlated with wealth, right? So social psychology predicts that there are different theories developed for this, but they basically suggest that indeed in these cases we can observe higher inequality. And finally, from behavioral economics, we're also interested in looking at what happens when your rewards are relative rather than absolute. So you can think here about like winner-take-all markets or sports context, where, for example, the difference between number 3 and 4 could be a matter of milliseconds, for example, in running, but in effect, the prizes could be, a huge difference. So that's what we're planning to explore, and to put it in a kind of in a game terms. I'm just going to give you like a kind of a funny idea we're having currently. So here's a game that's pretty much a version of kind of a mix between Tamagotchi and Farmville. Some of you remember Tamagotchi. So imagine you're a farmer and you have a crop, let's say corn, and you have some animals. I'm particularly interested in pigs in this case. And your goal is to grow a happy, healthy, fat pig that's gonna win the state fair. And you can feed your pig the crop you have, so corn, but to truly kind of thrive and be happy, you actually need to introduce some variety in the pig's diet, and so you need to trade with others, right? So, of course, you could exploit others, you can take more than you give, and so, your pig might get fatter, and you might win the state fair. So this is kind of, of course, we will kind of manipulate different aspects of what farmers see about other farmers, so how the state fair awards are given this could help us identify the structural conditions that we wanted to test. So we're very early in this process, and of course we're already kind of starting to think about some very concrete challenges about how do we implement this. The example I gave you with segregation, it was a very controlled situation where we had these high school students. They were not forced to be in the room, but of course there's kind of a pressure from their teacher to be in there, and they could not leave in a sense, or it was very rare that anybody left. But once you put this online with larger numbers of people, there's the problem of how do we bring so many people together? How do we keep them? How do we make sure they actually are engaged? And then, of course, there's also the problem of making sure that their engagement and their probability of staying is not correlated with the treatment, because some treatments might be more interesting than others, right? And then finally, also the problem with making sure that their outcome does not affect their likelihood to drop out, right? Because maybe the poor individuals experience the game differently than the wealthy individuals. And of course, there's also the problem of repeated participation, the fact that we have much less control online of who comes and how many times they interact. And so we are collaborating with Science at Home, which is at Aarhus University. It's actually the citizen science platform that was behind the quantum computing game that I showed very early at the beginning. And we're already kind of starting to think about solutions to these problems. For example, thinking about kind of having an event where we invite all the volunteers from the citizens platforms to come together and use it as a social event where they would play a game and then maybe talk about it afterwards, kind of, and reveal their identity. This possibility to, instead of trying to avoid repeated participation, to embrace it and put it into part of the design, where we would have both within subject and between subject designs analysis, where we can, by doing that, we can do this by basically routing newcomers to to the same world in a sense. So we can compare worlds of newcomers and also their worlds with repeated participations. So, so as I mentioned, this is all work very much in progress, and I'll be very curious about your comments and your impressions. And with that, I want to thank you for your attention and look forward to talking to you both now and in the break. Thank you.
Thank you for this talk. We have time for 2 questions. Yes?
Hello, I'm Pablo Jensen from France in physics, and I find this very interesting. I mean, the gamification idea, and the second question also about this inequality. And I had a comment on the first, because we have been working a lot as physicists on Schelling's model, but by simulating it and then showing actually with the utility function, that peaks at the mixed configuration, but then goes down. Mm-hmm. You can show that it's not only the simulations, but mathematically that you should find segregation there, even if it's counterintuitive. So it's, my point is, I share your concern that this can be used as a justification for segregation, whatever happens, but then why not use the simplest argument instead of putting people to follow exactly this artificial and strange utility function, so you force them in some sense to follow that. Why not argue simply that this is just too simple to mimic reality, so you cannot draw any social conclusion about reality when using such a simplistic model? I mean, it's a bit strange to put this simple model into reality to then argue that it doesn't apply to reality. I mean, this for a physicist is a bit strange, so I wanted to have your comment on that.
Yeah. Oh yeah, thank you. So so that's kind of we are in a bit of an interesting situation. So the Schelling model, as I mentioned, lots of people working on it, and there are a lot of extensions to it, right? So like a lot of the critique comes from the fact, this is very simplistic. We don't account things like, more than one ethnic group, or like the price of property and so on, right? So there have been like lots of extensions trying to kind of make it more sophisticated. So in our case, so we, in a sense, so there was kind of like a bit of debate, like, why are we doing this? Because, everybody thinks like, you're giving the utility of people, so of course, with testing is do people maximize their utility, right? But as we saw, actually, the reason for the results we saw was not from the utility, but it came from some of the other assumptions. And, I think theoretically, we could have really thought hard about these models and kind of found ways to to break them, to realize that, yeah, well, there is this assumption about, movement and ability to, evaluate the board, or like moving when, being able to recognize that you cannot improve your utility, that, if we relax it, it's unrealistic, and if we relax it, actually the model doesn't break. But, in this case, we decided to just kind of, to do the game, and that's how we discovered it, right? So, I think there is still some value of kind of doing this very simple experiment, I think we found something more than kind of the intuitive reasoning would have brought us pretty much. So.
Okay, are there any other questions? If not, then let's thank Milena again. And before you go to the coffee break, I just want to remind all of you, please fill in the survey. So outside there are some laptops. That would be really nice, because that would make the socio-patterns data much more valuable. Thank you.